Page 4 of Discrete Random Variables, number 7. Zeke is exploring a biased coin that lands on heads 0.964 of the time instead of a fair 0.5 and discovers something strange. Find the probability that the biased coin lands on heads exactly 4 and 5 times. Okay, so let's do that. So to do that, we find that the n is 5, right? And 4 is our x value, and since it says exactly, it's going to be PDF. And we are doing the biased coin, so that would be the p-value of 0.964. So let's put that in the calculator. So it would be binomial PDF, because we want to have exactly 4 times. So it would be 5, and p would be 0.964. And the x value would be 4. And we're doing PDF because it's exactly. And so the result is 0.155. Now it says to find the probability that a fair coin lands on heads exactly 4 and 5 times. So the only difference between this one and the other one is now the p-value is going to be 0.5. But we're still using PDF, right? So 5, instead of 0.964, now we're going to put 0.5. And everything else is the same. And the probability is 0.156. So the strange thing that Zeke discovered was that if you use a biased coin, or if you use a fair coin, which have totally different probabilities of turning up heads, they have almost the same probability that the head would turn up 4 and 5 times. Pretty weird, huh? Okay, now let's go to 7L. Given that the random variable x is binomial distributed with n equals 6 and p equals 0.29, find the probabilities. So they start out with an easy one. So that x is exactly 4, so that would be binomial PDF with n equals 6, p equals 0.29, and x equals 4. So let's do that first. Second distribution, we'll go to binomial PDF, which is option A, and we'll put in 6 for the number of trials, 0.29 for probability, and for the x value, we're putting in 4. And the probability is 0.0535. 0.0535. What about the probability that x is less than or equal to 4? So that would be binomial CDF instead of PDF, right? That's the only difference. So we'll go to binomial CDF. And then we'll have the same inputs here. Trial 6, p is equal to 0.29, and x is equal to 4, except now we're looking at x is less than or equal to 4 instead of x is exactly equal to 4. So we get 0.991. Okay. What about the probability that x is between 1 and 4? Okay, so this is a little bit tricky because we don't have a binomial CDF or PDF function that does this. P is 1 is less than or equal to x is less than 4. What numbers are we actually looking for? So that would be x is equal to 1, x is equal to 2, and x is equal to 3, right? So these are the 3 numbers that we're looking for. Do we include 4? No, because it's less than 4 and not less than or equal to 4. So there's like 2 ways to do this. One is you could find the probability that x is less than or equal to 3 and then subtract out the probability that x is equal to 0, right? So you would do CDF for this one, and then you would use PDF for this one, and you would subtract them. The other possibility is you could just use PDF 3 times, okay? And so we could do that. We'll just do PDF 3 times, okay? So we'll do a second distribution, and then we do binomial PDF, and the n value is 6, and the p value is 0.29, and the x value is 1. And that corresponds to 0.314. And what about x equals 2? And like if you're going to do something that's almost exactly the same, you could just copy and paste this and change the 1 to a 2. And that gives us 0.321. And then we could just go grab it again and then change the 2 to a 3. That would be 0.175. And so what we want to do is we want to add these 3 together. We could do that with copy and paste. Plus equals, so the answer is 0.809. Okay, and then the next one is, what's the probability that x is greater than or equal to 2? Remember, the calculator doesn't do greater than or equal to, so you need to reframe this as less than or equal to problem. So you do 1 minus the probability that x is less than or equal to 1. So let's do binomial PDF, or binomial CDF, right? Because this is less than or equal to 1. So we'll do second distribution, binomial CDF, and we're going to put 6, 0.29, oops, 6.29, and we're going to put 1. And the answer is 0.442. So we just need to subtract it from 1 now, because what we really want is greater than or equal to 2. We don't want less than or equal to 1. And the answer is 0.558. Okay, so that was greater than or equal to 2. Then we're going to do something which mixes this unit with the probability unit. So remember, the less than, not this bar here, the vertical bar here, means given, right? Conditional probability. So what's the probability that x is less than or equal to 4, given that x is greater than or equal to 2? And so if you look in the formula booklet, the probability that A given the probability of B is equal to the probability that both A and B happen divided by the probability that only B happens. So in this case, it's the probability that x is less than or equal to 4 and x is greater than or equal to 2, given that, or over the probability that x is greater than or equal to 2. Okay, so we just filled in the A's and B's with our situations. So the probability that x is greater than or equal to 2 and less than or equal to 4, let's see. We never calculated that, right? Greater than or equal to 2 and less than or equal to 4. So that would be the probability that it would be 2, 3, or 4 divided by the probability that it would be greater than or equal to 2, right? Probability that x is greater than or equal to 2. Probability that x is greater than or equal to 2, we already found that. It's 0.558. the probability that it's less than or equal to 4 and greater than or equal to 2, we could find that by doing the probability that x is greater than or equal to 4 minus the probability that x is greater than or equal to 1. Or the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 1. Wouldn't that give us the probability that it's 2, 3, or 4? Now, did we already calculate these? So less than or equal to 4 would be 0.991. Probability that x is less than or equal to 1, did we calculate that? Well, we used it here, right? There's less than or equal to 1, so that would be 0.442. So we could just subtract 0.991 minus 0.442. And that would give us 0.549. So that would be the numerator. The denominator would be 558. So it would be 0.4549 divided by 0.558. Which would be equal to 0.984. And that is the answer to part E, right? That is quite a difficult problem because it combines stuff that we've used a long time ago in the probability unit with things that we learned in this unit. F, use your answers to determine whether, now again, here we go back to the probability unit. So what is the definition of an independent event? Definition of an independent event is if the probability that both A and B happen is equal to the probability that A happens times the probability of B happens. This is what you're going to get from the formula booklet. So if it passes this test, then it's independent. Okay, so let's test that. So what's the probability that both x is less than or equal to 4 and x is greater than or equal to 2? So that would be this, right? It would be 0.549. So that would be 0.549. So that's the left side, and the right side is going to be probability of A times the probability of B. So that would be the probability that x is less than or equal to 4. Do we have that somewhere? Yeah, x is less than or equal to 4. And the probability of B is the probability that x is greater than or equal to 2, which is this one, right? So I'm just going to rewrite it here. So I'm going to rewrite it with the situations that we're looking at. So probability of A intersect B is the probability that x is less than or equal to 4 and probability is x is greater than or equal to 2. The probability of A is the probability that x is less than or equal to 4, and the probability of B is that x is greater than or equal to 2. So let's check this. So the one on the left we saw is 0.549. And the one on the right is x is less than or equal to 4 is 0.991. And then greater than or equal to 2 is 0.558. And so now what we're going to do is we're going to test to see if 0.991 times 0.558 is equal to the left side. So 0.991 times 0.558 is 0.553. So they are not equal. So it's not independent. Okay. G, find the expected value of x and find the variance of x. Okay, so these are some of the easiest kind of problems as long as you recognize what kind of problem it is. Okay, so if you look at the formula sheet for part G, there is a formula which is that the expected value of x is equal to NP. So in this case, we already know what N and P are. They're given right here. So if we recognize that this problem is when you're supposed to use NP, it's quite easy. You just take 6 and multiply it times 0.29. That will give you the expected value. So the answer is 1.74. And then for part H, which is the variance, then what you're looking for is you're looking for the formula in the formula booklet, which is NP times 1 minus P. And so again, you already know N and P, so this is quite easy. 6 times 0.29 times 1 minus 0.29. So we can do that pretty easily too. And 0.29 times 6, we already did that, it's 1.74. We just grab that, and then we multiply it times 1 minus 0.29. $1.235 or 1.24. Okay, so that's the variance. And variance, if you're interested, is actually equal to the standard deviation squared. So if they ask you for standard deviation instead of variance, then you just take the square root of it, because variance is standard deviation squared. Okay, all right, let's go to the last one. So I'm just going to put a line here to divide one problem from the other. A biased coin is colored red on one side and black on the other. The probability of throwing red is 0.78. In 10 throws of the coin, find the probability that exactly 3 blacks are thrown, and the number of reds thrown is more than 3 but fewer than 7. Okay, so let's see. I am going to data collection part of this problem. So let's look at the first scenario. It says, what's the probability that 3 blacks are thrown? And this is a little bit tricky because if you look at what the information they gave you, the p-value they gave you is related to throwing a red. And they're asking what's the probability that we get exactly 3 blacks. So remember that the coin is red on one side, black on the other. So if the probability of throwing a red is 0.78, the probability of throwing a black is the opposite, which would be 0.22, right? 1 minus 0.78. So the probability that you get 3 blacks is going to be using the n value they gave you, using the p-value you calculate, 0.22 instead of 0.78, and the x value of 3. And of course you're going to use PDF because it's exactly 3 blacks. So let's do that. Second distribution, and we'll go to PDF because it's exactly. And we're going to put 10 and 0.22 and the x value of 3. And we get 0.224. Okay. And then we want to find out the number of reds, the probability that the number of reds thrown is more than 3 but fewer than 7. So that x is between 3 and 7. And in this case, we're talking about reds. So what's the probability that the reds are between 3 and 7, not including 3 and 7? So to do that, the calculator can't do between two numbers. It can only do less than or equal to. So we need to set this up as the probability that x is less than or equal to 6, right? Because between 3 and 7, not including 3 and 7, would be 4, 5, and 6, right? So we want the probability that x is less than or equal to 6 minus the probability that x is less than or equal to 3. If we do that, then we're left perfectly with the probability that x equals 4, 5, or 6. So let's find the probability that x is less than or equal to 6. Obviously, we're going to use binomial CDF. And in this particular case, do we want probability equals 0.78 or 0.22? Since it's red, we're going to use 0.78. So 10.78, and we're looking for 6 first. We're doing CDF, so this would be 6 or less. and it'd be 0.159. And then the probability that x is less than or equal to 3, we could just copy this and then change the 6 to 3. And that would be 0.00158. So if we wanted to find the difference, we just do .157. Okay? All right. Now let's read the bottom part. Let A represent the event that fewer than 3 blacks are thrown, and B represent more than 7 blacks are thrown. Okay, find the probabilities for A, B, and A given B, and then find out if the probabilities are independent or mutually exclusive. So the first part, you're actually using binomial PDF and binomial CDF. The last part is a review of probability. Okay, so first of all, let's find the probability of A that there are fewer than 3 blacks are thrown. Okay, and remember, blacks, the probability is going to be 0.22 instead of 0.78. Okay, so the first one, probability that fewer than 3 blacks are thrown, would be x is greater than or fewer than 3 blacks. So that would be fewer than 3, but that would be equal to the probability that x is less than or equal to 2, because the calculator does less than or equal to. It doesn't do less than, right? And that would be A. And the B scenario is that the probability that x is more than 7, which is equal to the probability that equal to the probability that of 1. Oh, come on. Okay, there's a problem. 1 minus the probability that x is less than or equal to, So x is greater than 7 means 8, 9, 10, blah. So if we want to get rid of the 0 through 7, we need to do x is less than or equal to 7 for what we subtract out. Okay, so what is the probability that x is less than or equal to 7? What is the probability that x is less than or equal to 2? Let's calculate those on the calculator. So we'll do that by second distribution. And we'll go to binomial CDF because we're looking for less than or equal to. And we're going to put trials 10. And the probability is going to be 0.22 because we're talking about black here, not red. And we'll do less than or equal to 2. And so the probability of A is going to be 0.617. And then the second one is 1 minus the probability of less than or equal to 7. So instead of 2, we'll put 7. .99984, okay, and then 1 minus, and then we'll subtract out that. It's going to be something really small. It'll be 0.000160, 0.000160, or 1.599 times 10 to the negative 4th. Okay, so we have our A and B. Then it says find the probability that A given B. So the probability that A is given B is equal to the probability that both A and B happen. Remember, this formula is in the formula booklet. Probability of both A and B happening means it's the probability that x is less than or equal to 2, and it's less than or equal to 7. Well, the thing is, x is less than or equal to 2, and x is less than or equal to, probability that x is less than or equal to 2, and x is greater than 7, both happening? Well, actually, the probability that x is less than 3 or less than or equal to 2 and the probability that x is greater than 7 both happening is 0, right? So the probability of A intersect B divided by probability B is going to be 0 divided by, something that's not 0. So it's just 0, okay? So the probability that A given B is 0. Okay, so now, are the events A and B independent? So the test for independence, remember, is to do the probability of A times the probability of B and test to see if it equals if it equals both A and B happening. A and B both happening, the probability is 0, and the probability of A happening is 0.617, and the probability of B happening is 0.000160. Multiplying those two together is not going to give you 0. So no, it's not independent. Are they mutually exclusive? So is the probability of A happening completely separate from the probability of B happening? Yeah, that's true, because the probability that, now remember, the definition from the set point of view of mutually exclusive is that the intersection of the two sets is equal to 0. And in this case, we just talked about how the fact that the probability of both of them happening is 0. So yeah, the probability of both happening is 0. So it is mutually exclusive, yes. Okay, so the first part, like I said, is a binomial distribution problem. The second two is checking your understanding of just probability.